All right, so here what we're going to do is we're going to learn how to graph absolute value signum as piecewise functions. So what we're going to do is we're going to graph something that looks like this. Now, instead of making a table of values, what I'm going to do is I'm going to break this up into three pieces. So how do I think of the absolute value graph being uh, a piecewise function? Well, let's think about the parent function. So here's what absolute value of x looks like. So when x is greater than 0, we're dealing with this part of the line here, which is literally just a line of x. So if x is positive, we can just think about it being the line x. Well, when x is 0, we're talking about this point here, which is going to be 0 on the parent function. But what kind of line do I have when x is less than 0 over here? Well, that's a line negative x. It has a -1 slope. So this is the absolute value function broken up into three pieces. When I introduced you to signum a few days ago, we talked about how signum is that weird looking graph where it outputs 1 when it sees positive numbers, it outputs 0 if it sees 0, and it outputs -1 when it sees negative numbers. So how do I help or do that to help me do something that looks like this? Well, I'm going to break this up into three pieces. I'm going to do a little bit better of a bracket there. It's somewhat better. When x is greater than 0, when x is positive, when x is 0, and when x is negative, less than 0. So what I'm doing is I'm taking the absolute value function and subtracting the signum function. Well, when x is positive, the absolute value function is x. When x is positive, signum gives you 1. And if you're going to subtract these two, because based on the problem, we just get x minus 1. So that means the piece of this graph is going to be x minus 1 when x is greater than 0. So it's going to be kind of an open circle here. It has a slope of 1, and it just goes on forever like this. Well, when x is 0, this is when you have to be very, very understanding of what's happening here. We are literally plugging in 0 into the absolute value, which we get 0. We plug in 0 into signum, get 0. And if you subtract 0 and 0, you get 0. So you get a point there. What about when x is less than 0? Well, when x is less than 0, the absolute value function is negative x. Signum is -1. And if you're going to subtract these two pieces, well, we end up getting negative x plus 1. So this is that piece of the function. So when x is less than 0, it's the line at negative x plus 1. So it has a y-intercept at 1, has a slope of -1, and it's talking about less than 0. So we're talking about everything that's to the left of 0. So this is your introduction of how we graph the absolute value of x minus signum of x using piecewise functions. Now, what happens if I have something that's added or subtracted to this x? Well, if I set that x equal to 0, well, then we end up getting -3. I can change that equal sign to less than or greater than, and it's going to be less than -3 and greater than -3. So our restrictions on our piecewise functions are going to be of values -3 instead of 0. So it's going to be the same kind of process. I'm going to break it up into three pieces. I'm going to do the negative of this version. So I replace the absolute values with parentheses, and I'm going to put a negative in front of it and the rest of the equation. So we end up getting -x minus 3 plus x, which ends up giving us -3. And that happens when x is not less than 0, because our 0 in this case is -3. So for all our values that are less than -3, we have a value at -3. So that piece of the function is just this horizontal line. Well, in the next case, I would plug in x is 0, but my new 0 in this case is -3. So I'm going to plug in -3 for every x that I have in here. And I can leave off the absolute value because it's not going to change anything. You can put it there if you want to. So we get 0 minus 3, which is -3. So that means when x is -3, this function is at -3, which kind of happens here. So originally I should have probably put an open circle there, but I knew it was going to come out to be closed either way. So if you have an open and a closed circle in the same spot, then it's automatically closed. Well, when x is greater than -3, we just take the absolute value bars away. So we kind of get x plus 3 and then plus that x. So we end up getting the line 2x plus 3. Well, what's nice is that when I plug in -3, I actually get out -3. When you plug in -2, because that's the next number that's bigger than -3, you end up getting -1. And when you plug in 1, you get out 1. Or plug in -1, you get out 1. And so then you kind of have a line there. That line just has a slope of 2 instead of just being a horizontal line at -3. So same process. Again, we're going to take the negative part of the absolute value. We plug in our 0, and then we take the absolute value bars away whenever our value is greater than that 0. So what about 3 here? Notice that it's just the absolute value of 2x. So my 0 would still be 0. So instead of dealing with -3, I'm going to just deal with our x is less than, equal to, or greater than 0. So my 3 pieces for this graph, so I'm going to do the negative version of that. And that ends up simplifying to 2x minus 1 when x is less than 0. So for this one, I kind of showed it that, if we're doing x is strictly less than 0, that would create an open circle for this piece of the graph that starts at -1 and has that slope of +2. Well, if we end up plugging in 0 for every x that I see, and again, the absolute value bars around that is not needed, we end up getting -1. So that means that x equals -1, we end up having a point at -1, which makes it full. So that's what I kind of talked about over here. And then when x is greater than 0, we end up just taking away the absolute value bars and simplifying the equation. And then we have that piece of the graph that starts at -1 and then has a slope of 6. So I did add a few numbers on my axes just to kind of show y'all where those numbers are. So again, just breaking these up into smaller pieces so that it's easier to graph instead of just plugging in values into these for x and y and not knowing where the middle is or where it's starting and all that good stuff. So make sure to just practice that. So the next thing that we're going to review are graphing rational functions. So we have vertical asymptotes. Asymptotes are invisible lines that our graphs never cross. So vertical ones are going straight up and down. So those are values of x's that create my function to be undefined. So to find those vertical asymptotes, what we're going to do is we're going to set the bottom equal to 0. Our horizontal asymptotes have rules. So if the degree on the top is smaller than the degree of the bottom, then our horizontal asymptote is at 0. If the degree of the top equals the degree of the bottom, then what we do is we take the leading coefficient of the top and divide it by the leading coefficient of the bottom. Well, what if we have it where the degree of the top is bigger than that on the bottom? Well, that means we don't have a horizontal asymptote, but it might be possible that we have a slant one. Okay. So 3 different rules here. So the degree of the top is smaller than the bottom, we get 0. If the degrees on the top and the bottom are the same, then we divide their leading coefficients. And if the top is bigger than the bottom, there's no horizontal asymptote, but there is a possibility of having a slant one. X-intercepts is where it crosses the x-axis. We can sometimes call those zeros. So in a fraction, the only part of the fraction that can be 0 is the top. So we're going to set the top equal to 0. The y-intercept is where it crosses the y-axis. So you're going to plug in x is 0 and figure out what the y-intercept is. So those are our rules. So let's actually apply them. So we have number 3 here. So what I always like to start off with is try to factor it as much as I can. So the top cannot be factored, but the bottom can be. What that helps me do is easily solve for zeros or x-intercepts. So my 0 is setting the top equal to 0, so it's negative 1, 0. Why don't I put x equals negative 1 here? Well, zeros, x-intercepts are points. If I ask you to plot negative 1, what do you mean? If I tell you to plot the point negative 1, 0, you're like, oh yeah, that's right here. Sweet. The next thing I always like to look for next are my vertical asymptotes. So in this case, we have negative 2 and positive 2. So I'm going to put plus or minus 2 on my paper. So that means why do I have x equals here? Well, x equals are vertical lines, which are what asymptotes are. They're vertical lines. So what I'm going to do is I'm going to draw, negative 2 and positive 2, and I'm going to draw my asymptotes, which are going to be dashed lines. Then I usually like to find my horizontal asymptotes next, which the degree on the top is smaller than that on the bottom, so our horizontal asymptote is automatically at 0. And as you can see, I'm going through each time and drawing what I have found. Then, what can I find next? Well, my y-intercept is plugging in 0 for every x that I see, and you end up getting negative 1/4. So our y-intercept is going to, if I say 1 is here, then negative 1/4 is about here. All right, so I kind of know that I should never cross vertical asymptotes, so I'm going to connect these dots so you can kind of think, okay, well, if I'm going to connect those dots and it never crosses a vertical asymptote, we get that piece there. But where's the rest of the graph? Well, we can use the wave in order to figure out where my graph is above or below the graph. So with quadratics and polynomials like this, these are kind of a rough sketch of what your graph looks like. But here, they're not going to be a sketch of the graph. They're going to tell you where the graph is positive or negative. So I need some critical values on my x-axis that can tell me where my sign changes. Well, some critical x values that I have here are negative 1, negative 2, and positive 2. So I'm going to make sure I put that in order on my number line. And again, you can put 0, 1, you can put whatever numbers you want on here. Critical points are the most important. So same idea with the wave. You look at the leading coefficients. The leading coefficient on the top is positive. The one on the bottom is positive. So we're going to start up here. We don't have to worry about less than or greater than or equal to or anything here because we're just trying to see what happens at these values. Well, since these are all single critical points, we're going to go through each one of them. So this is what my wave ends up looking like. So this wave is telling me that my y values are positive to the right of 2. They're negative between negative 1 and 2, which makes sense that, hey, my y values are all going to be negative between negative 1 and positive 2. It's positive up here and negative here. So we end up getting, if it's positive to the right of 2, our graph looks something like this, and it's going towards those asymptotes. We already got this piece. Between negative 1 and negative 2, all my y values are positive, so it's up here. But then to the left of negative 2, all my y values are negative. So if you want to be a little bit more exact, you could try to plug in numbers that are to the left of negative 2 and plot some points, but all we really need is a sketch and definitely plotting all of this information here. Well, this next one's very awesome because it's already all factored out for us, so less work for us to do. The thing here is that I have multiple zeros. I have negative 1, 0, and I have 3, 0. So negative 1 and then 3, those are points. My vertical asymptotes are what sets the bottom equal to 0. So we have 4 and we have negative 2. So negative 2 and then 4 and then our vertical asymptotes. Well, then my horizontal asymptote, well, the degree on the top is x squared. If we follow this all out, the bottom is x squared. So they're equal. So we divide the leading coefficient by the leading coefficient and end up getting 1 is my horizontal asymptote. And then if you go and find the y-intercept, you plug in 0 for every x that you see, you end up getting negative 3 over negative 8 or positive 3/8. So somewhere, here. So you can kind of think, okay, well, I'm going to have to connect these 3 dots. So it should look something like this, but where's the rest of the graph? You can kind of think, okay, well, it's going towards that asymptote there. It's going towards this asymptote here. But how do I know for sure where the rest of my graph is? Well, let's do the wave. Our important x values that we're dealing with are -2, -1, +3, and +4. Our vertical asymptotes and our zeros. Since our leading coefficients are both positive and all of our critical points are single roots, that's what our wave looks like. So to the right of 4, it's above the x-axis. All my y values are positive. Well, between this x-axis and the horizontal asymptote, it's y values that are positive, but there's no way for my graph to go. If I start drawing my graph, it's going to end up going towards the vertical asymptote and becoming negative. So the only place where it's above the x-axis that I can actually draw a full graph that flows well towards each of those asymptotes is up here. Between 3 and 4, all my y values are negative. Sweet. I kind of predicted that just by connecting the dots and going towards the asymptotes. Between -1 and 3, all my y values are positive. Between -2 and -1, they're negative. And then to the left of -2, they're always positive. And so that we have a nice graph that flows, we put that last piece there. So the last thing that we're going to talk about in these sets of notes are called holes. Holes are where the original function is undefined. So there's going to be a certain x value that creates chaos in this problem. So the way that we're going to do that is, just like what we talked about on the last page, we're going to factor the top and factor the bottom. So the top ends up factoring out to this, and the bottom ends up factoring out to this. Wait a minute, the x minus 2's, they're both on the top and the bottom, so what we end up having is we're going to end up having a hole where my x value is at +2. Why +2? Well, if you set these equal to 0, you end up getting +2. Now, depending on your Algebra 2 teacher, sometimes they just say, oh, well, wherever your graph is at 2, just draw a circle. Well, in this class, you're going to end up having to tell me what the y value is there. So all the rest of my information that I'm going to be getting is going to come from this simplified version. So if you plug in 2 into this simplified function, you end up getting 1/5. So we're going to have an x value of 2. This is 1. And so 1/5 is going to maybe be somewhere here. And you draw an actual hole, an open circle in your graph. If we were just graphing x minus 1 over x plus 3, it would almost look like the exact same graph without a hole. But we are graphing this original function. This original function has a hole at 2, 1/5. I know 1/5 can be 0.2, but leave your answers as fractions. Don't ever go in an extra step, especially on an AP test. If you go that extra step and you do that wrong, then you don't get any points for that. So just leave it as fractions. Make sure it's always reduced for our class. All right, so let's go back to what we talked about on the other page. So if I'm going to look for a 0 here, that's going to be at 1, 0. So here's a point. Then our vertical asymptote is what makes the bottom equal to 0, which is -3. So 1, 2, 3. The degrees on the top and the bottom are the same, so we divide the leading coefficients and get that our horizontal asymptote is here at 1. And then our y-intercept is going to be here at 0, -1/3. So we say that's 1, so -1/3 maybe looks like that. So it's easy to figure out where the rest of this is going, or how this is all going to connect and go towards the asymptotes. And remember that we're drawing functions here. You have like 3 other quadrants that this other piece can be in. It can't be up here. If I draw a piece of the graph up here, that's not going to be a function. There are times where your piece of the graph is going to go here, but there's no other 0. We're not crossing the x-axis anywhere. Well, the only other place that our graph could be is up here. And again, you can plug in some numbers if you want an exact point, but that's that. You can also do a wave where we're doing just the 0 and the vertical asymptote, so -3 and 1. And the leading coefficients are positive, and they're all single roots, so you do that. So to the right of 1, it's above the y-axis, check. between -3 and 1 below the y-axis, check, and then above the y-axis to the left of -3, which works. Then what about this last one here? Well, it's nice and factored out for us. So let's figure out. So there's nothing that eliminates, so there's no holes. I have two x's up here on the top, so I'm going to have two zeros. I'm going to have one at 0, 0, which makes that x equal to 0. You could kind of factor out the 2 here if you wanted to, but you don't need to. But we end up getting that we have another 0 at +2. So we have one here at the origin, and then we have another 0 here at +2. Then our vertical asymptotes, we have x minus 4 squared. Well, that means that I'm going to have x equals 4 twice. So instead of writing x equals 4 twice, we're going to put double root. So 3, 4, and I'm going to draw my vertical asymptote. Well, what about my horizontal asymptote? Well, the degree at the top is x squared. The degree on the bottom is also going to be x squared if you FOIL it all out. But the leading coefficient on the top is going to be 2. The bottom is 1. So you end up getting that your horizontal asymptote is at y equals 2. So y equals 2, and then we draw our horizontal asymptote. And then what happens for our y-intercept? Well, if we plug in 0, we end up getting out 0. We end up getting out 0 over 16, which is still 0. So this is all I have. How do I know what my graph looks like? Well, if I use my wave, I have 0, 2, and 4 as my important x values, my critical points. Since the leading coefficients are both positive, we're going to start up here, but 4 is a double root, so it's going to bounce off of 4 and through 2 and through 0. So to the right of 4, it's always above the x-axis. So we end up having a piece of the graph that's up here. Between 2 and 4, it's also above the x-axis. And you end up getting this piece of the graph. So it needs to go towards the vertical asymptote. And you might be wondering, it's like, wait a minute, I can cross the horizontal? Horizontal asymptotes are used to figure out end behavior. What is happening to the graph as x gets bigger and bigger and bigger, or smaller and smaller and smaller? Anything can happen in the middle. So you can cross your horizontal asymptotes anywhere in the middle of your graph. It just can never cross a vertical asymptote. You can never cross a vertical asymptote. So then between 0 and 2, it's below the x-axis, so it comes up this way. And then above the x-axis to the left of 0. And again, horizontal asymptotes are for end behavior. There might be some cases where it crosses the horizontal again and kind of does some crazy stuff here. But this is a rough sketch. All we really need to make sure y'all understand how to do is to go towards that horizontal asymptote at the end. Okay, so as x gets bigger and bigger and bigger, it's going towards this horizontal asymptote. As x gets smaller and smaller, it goes towards that horizontal asymptote. If you have any questions, make sure to ask. See ya.